Physics, electricity. Today we shall be looking at calculations involving electrical circuits. And a circuit is just an interconnection of elements to form a closed loop in such a way that current can flow across the circuit. Now we have some components that make up these circuits. First of all, we have a source of battery, which is represented thus, the larger side being our positive terminal and the smaller side being our negative terminal. And this is what we use to supply direct current voltage. Then we have another source, which is our alternating current source, and that is used to that's represented thus. And we can find that when we look at our sockets, the sockets we have in our house, they supply AC, and that is how we represent, that's the symbol for representing AC supply. Then we have a source of current represented thus. A represents current, and then that is the way we represent a current source. So these are sources of power or sources of energy, as the case may be. Then we have our next element is the resistor, represented in two ways, as we can see on our screen. Okay, so these are the two ways we represent our resistors R. Then our next element we'll be looking at is the inductor L. Our inductors are represented with the symbol, as we can see. I'll just draw that now. Okay, this is the symbol for our inductors, L. And then the next one is our capacitors, which represents, looking similar to the battery but different in the sense that the capacitors have equal length of the vertical lines. You can see those lines are equal. For capacitors that have polarity, we can represent them in another way. We can make the bar, one of the bars, thicker, and the thicker one is what we call our positive terminal. So I'll just draw that for us to see now. Okay, so a capacitor, I said that we use C to represent a capacitor, and for the one, let me draw the one for the polarity, the one with polarity now. We have a thicker bar for the positive side, and then we have a thinner bar for the negative side. But remember, the height of the negative and positive are still the same. So that is how we represent capacitors with polarity. I'll just color this now to make it look better. Okay, so that is how we represent our capacitors. Now that we've drawn some of the symbols of some of the elements that will be seen in electric circuits, let us go straight into solving the question we have on the screen. So we are told that a storage battery has an EMF of 25 volts and an internal resistance of 0.2 ohms. Compute its terminal voltage when it's delivering a current of 0.8 amperes. A storage battery has an EMF of 25 volts and an internal resistance of 0.2 ohms. Compute its terminal voltage when it is delivering a current of 0.8 amps. We know that there is a way we represent our voltage and our current in terms of resistance based on Ohm's law. But before I go into that, I would just like to draw the diagram. And the question says we have a 25 volt source, which has an EMF of 25 volts. So that is represented as that on the screen. Then that battery has an internal resistance, and we'll use small letter R to represent that internal resistance of 0.2 ohms. So this is from our source. This is what they are asking us for terminal voltage. So our I is equal to 0.8 amps, and then we have that we are looking for the terminal voltage. So what is the voltage when it is when we connect a voltmeter across the terminals of this socket, of this circuit, I mean. So we have a voltmeter connected across there like that. So what would this our voltmeter measure? That is what we are looking out for. The small internal resistance R is responsible for internal losses inherent in the battery. So based on that, we can write our formula as E, the rated voltage of the battery, EMF of the battery, is equal to IR plus V. IR is the voltage drop as a result of internal resistance, and then V is our terminal voltage. IR is voltage drop as a result of internal resistance. So now that we have that formula, we can go ahead and fix in the information that we have into the formula and then go ahead and solve it. Okay, so we have that E is equal to 25 volts, and then I is equal to 0.8. So 0.8, we write 0.8 times 0.2 plus V. So V is equal to 25. When the 0.8 times 0.2 crosses over the equal to sign, becomes minus. So 0.8 times 0.2 is 1.6. So V is going to be equal to 25 minus 1.6, which will give us 23.4 volts. Very easy, right? So let's look at this second question. It says, a current of 1.5 amps exists in a conductor whose terminals are connected across a potential difference of 100 volts. Compute the total charge transferred in 1 minute, the work done in transferring this charge, and the power expended in heating the conductor if all the electrical energy is converted to heat. So we are looking for three things there. First of all, we are looking for our quantity of charge, Q. Then we are looking for our work done, W. And then we are looking for power, P. I'll use P to represent power that we're looking for. So those are the three things the question is asking us to look for. So how do we go about the first one? Q, to find the quantity of charge. There's a formula for finding quantity of charge. Quantity of charge, Q, is given as Q is equal to IT, where I is our current and T is the time at which that current passed through that particular point we're looking at. So T is the time it passed through. So Q is equal to I is 1.5. And then we are told that our T is equal to, we're told that T is equal to 1 minute, flowing for 1 minute. But we know that the minute is not the SI unit for time. So we have to convert our time to our SI unit, which is in seconds. So 1 minute is equal to what? 60 seconds. 1 minute is equal to 60 seconds. Now that we have that, we can put that 60 seconds into our equation, and we have that Q is equal to 1.5 times 60, and that should give us 6 times 15 is 90. So 60 times 1.5 is also 90. So that's going to give us 90 columns. 90 columns. Now the B part says, what is the work done in transferring this energy? Work done is depicted as W, and W is equal to P times time. That is, power times time gives us work done. Therefore, P is equal to W over time. So that means we can define power as the time, as the rate at which energy is being consumed or created based on this formula here. We can say power is defined as the rate at which energy is expended or created. So with that in mind, I would like to work for power first, and P is equal to IV. P is equal to IV. We know what our I is, and we know what our V is. So P is equal to I is 1.5, and then V is 100. So our power is going to be equal to 1,500 watts. 1,500 watts. And we can write that as 1.5 kilowatts. Okay, now that we've done that, we can now go straight to solving for the work done, W. Remember, we said that work done is equal to power times time. Power times time will give us work done. So now that we have our power as 1500 watts, we can say our work done is equal to 1500 watts times 60, and that is going to give us 6 times 15 is 90, so that will give us plus the 3 zeros, that will give us 90,000 joules. 90,000 joules, and we can write that as 90 kilojoules. W is equal to 90 kilojoules. So that is solved.